Today we will speak about multi-objective optimization algorithm. So we'll speak about PESA2. So Pareto Envelope based selection algorithm version 2. In the input parameter of the script, we have or the user have the possibility to introduce the number of iterations, the population size of the internal population, the population size of the external population, which is the archive, and also it has the possibility to introduce some variables, defining variables for the test function. So the algorithm comes with a subscript mo test function, multi-objective test function, which is updated with 16 test functions, and also the constraints of equality and inequality are applied here. Okay, so for our demonstration we were going to use the fifth test function with the lower and upper bound -5, 5. Number of decision variable is 3, number of objective 2. So at test function number 5 we are going to see that number 5 is the Cursave test function. Yes, so it's the Cursave test function. Let's see how it looks like. So here it is. We at the end of the optimization we should have a graph like this one. Okay, so this algorithm uses the mechanism of genetic algorithm, the crossover and the mutation. It has two, as I mentioned, two populations, one internal population and one external population. The archive, the chromosome for breeding and mutation are selected from the archive based on the grid. This grid defines the geographical distribution of the archive's member. So the grid is divided by boxes or squares, in which each of the box of the grid have an attribute called the squeeze factor. This squeeze factor represents the number of chromosomes that inhabit the same box or square. This attribute squeeze factor is used in two ways. One way is used for selective fitness. I mean, in tournament selection, the algorithm chooses the chromosome with the lowest squeeze factor, and also the archive update in order to update the archive of the algorithm. The algorithm will delete the chromosome with the highest squeeze factor. Further, we are going to see how the algorithm works. So first of all, a population is created, a random population with random values from the definition domain. So in this way, the position or the internal population is created. This position matrix is going to be evaluated. This population is going to be evaluated according to a multi-objective test function, as we mentioned earlier. And the values of the objective functions are going to be written in the cost matrix. Then further, we are going to enter in the main loop of the algorithm. So for every iteration is going to be determined the domination. So which chromosome is going to be dominated and which not. Then update archive. In this stage is going to be created the second population, the archive or the external population, which consists only with non-dominated solution from the previous population. Once again, is going to be determined the domination. Then another step is keep only non-dominated solution. So after the domination is going to be determined, the algorithm will keep in the archive only the non-dominated solutions. Then very important step is going to take place to create the grid. Yes, and further at every iteration the algorithm will plot the objective functions in the Cartesian display. Then the crossover is going to take place, selecting two individuals based on the grid determined. Going to select two individuals, and is going to cross over and to form another matrix, C position, so crossover position. In the next stage, the mutation is going to take place, in which also is going to be selected a member to mutate, and the M position or mutate position is going to be created. In the next step, the initial population, the internal population, is going to be reconstructed by concatenating the two previous population, C position and M mutation. And this new position matrix is going to be once again evaluated by a multi-objective test function. So these steps are going to be repeated until the maximum iteration is going to be met. We have here another step in which if the archive is full, then the population is going to be truncated once again according to the grid, to the grid that we created. Now we are going to run the algorithm with these settings. So we are going to use 50 iteration with number of population. Let's say 300, with the number of archive 100, number of objective 2, number of decision variable 3, lower upper bound -5, and test function 5. Test function 5, Cursave test function. So once again we will obtain something like this. This is the plot for Cursave function. Okay, so let's run the algorithm. So you can see multi-objective plot popped out with the Pareto front. You see that it is taking shape like the one in literature. So we can see that at iteration 22 we have already 100 members. So at this stage the archive is going to be kept at 100. Okay, we will wait to see what is happening. We can see that it resembles more and more like the literature. So we can see that in literature we have at a point here at -20, 0. We see also we have, so okay, yeah, the algorithm finished. It took almost a minute to finish. You can see here at -19.98, almost 20, and 0.02, almost 0, we have a point, and then another point here at -19, almost 19, and almost 0, exactly like in literature. We have 3 fronts, exactly like in literature. Okay. Further, we are going to try to optimize 3 objective test functions. So let's go and select an 3 objective test functions. So going to subscript mo test function, we are going to use the 16th test function with the low and the high -2 and 2. Okay, so we're going to write here 16, 2, and -2. So number of decision variable is going to be 2, and number of objective function is going to be 3. Yes. So save, but we are going to use a population of 600 with 500 Pareto front. So we are going to run this algorithm, the script. Let's see what is going to happen. Okay, we see that the algorithm runs, and here we have the plot, but the plot is only for first for x and for y variables. The third variable z is not going to be displayed here because the DIgSILENT doesn't permit to plot 3D objective function. Okay, so we are going to see at the end of the optimization what is the final result. And also I created a script here, 3D, in which a 3D scene is going to be mapped in a 2D surface. So we are going to use the values for the three objective function for x, y, and z, and we are going to make a 2D plot, and that looks like a 3D one, if you know what I mean. But this we are going to see at the end of the algorithm. Okay, so the algorithm finished its work. So it took about half an hour in order to finish. We can see here, once again I repeat myself, this is a 2D plot. So here is plot only the first two objective functions, the cost. So a cost. So here we have on the x-axis, on the y-axis. So first two columns are displayed here in this plot. The third one, which gives the deepness, the 3D effect, the third dimension, is not represented here because DIgSILENT does not have such possibility. In order to solve this, I created a script in which we are going to see a 3D interpretation or a 2D representation of the 3D space. So we have here 3D, in which we have as an input the a cost function with three columns, and those three columns are going to be interpreted by this algorithm in 2D space, and we will see like a 3D image. Okay, so let's see, spin 3.14, this spin 001 is okay. So let's run to see how the graph is going to be spin around x-axis. Yes, and we are going to see the 3D representation. You see? So this is the representation in 3D of the solution of the three objective functions. Yep. Yeah, so so that's it.